Jay, we didn't need that.
I love writing.
I'm pretty sure.
All right, so
Tangential.
tangential.
What time?
That's how I
Say
say
it
it.
again.
Time.
Tangential.
Now I'm second. All right. So let's check this out. All right. We'll work through this one together, maybe through a few conceptuals. We'll see how far we get here. So let's see. A grinding wheel starts at rest, okay, and accelerates uniformly for 10 seconds and reaches its maximum speed of 25 radians per second. The wheel runs for another 37 seconds and then shuts off. The wheel decelerates uniformly at 1.5 radian per second squared. Yeah, I don't know. Until the wheel stops. What is the time interval that it takes the wheel to slow down? Okay, so we have two things we got to look at. What all information do we know?
Time.
Okay, we know. So we know time. A grinding wheel starts at rest and accelerates uniformly. So we know it's acceleration, and like its start, right? We know the initial acceleration times 10 seconds. Okay, so we know that. Let's write that. What else do we know?
You know the initial omega.
Initial omega is 0. Okay. Let's see. We know my final omega, right? Final omega is 25, right? All right, so then the wheel runs for another 37 seconds and then shuts off. The wheel decelerates. Okay, so in the deceleration, right, we know our alpha. Working on it. All right, so we know my deceleration, so my alpha is negative 1.5. Oh, radians. Holy smokes, radians. That was a good save. Per second squared. Okay, so we know alpha. We know what my final is going to be. Right? It's eventually going to go down to 0.
We like zeros.
And we actually know what my initial, when it starts to slow down, is going to be. What's that going to be? 25. Holy smokes. So we're doing pretty good so far. We got a lot of information. Okay, so it says, what is the time interval that it takes the wheel to slow down? Okay, what is the time interval it takes the wheel to slow down? What equation do you think we're going to use? So we need to find this time over here. Okay, we can definitely use that one. Absolutely. Okay, so omega final 0 is equal to omega initial 25 plus alpha times time.
We can't see that.
I didn't want you to see it.
Oh.
Alpha times time. Absolutely. So when we solve for time, we plug it in. What you guys get? 17?
Oh my gosh.
What are the odds of that ever happening?
Wait, why would we need all of the left side then?
Yeah. I mean, in theory, you don't. I'm just writing down all the information I know.
So the 37 seconds, really the 10 seconds.
It runs for 37. Yeah, that's all. This applied to the next side. But other than that, we didn't really need all of that or that. Just writing down everything the problem has for us.
Oh my.
Right.
Is that a problem? Yeah.
I know this is a stupid question, but can you like figure out the units for your answer by just like figuring out what's dividing what?
Yeah. Okay. Next question. So we have some conceptual problems coming up. And I really want you guys to think about it before answering. All right? Some conceptual problems. A rigid body accelerates about a fixed axis. All right? All the points in the body have the same what? Really want you to think about this. All right? Hopefully you remember all these terms. What do you guys think the answer is? Anybody want to take a shot? B or C? Anybody else want to take a shot?
It's one of the A, B, C.
I'm just kidding. I would listen to Taylor. It's one of those two.
The way that I took it down is because I knew it was one of the accelerations because there's 3 of them. That's obvious. And then centripetal needs radius, but since it's rigid, you can't use radius, right?
Let's get rid of B. Let's get rid of D. D's linear. We don't really worry about linear. A, tangential speed. Okay? Tangential speed. All right? Let's get rid of the speed. Now, do we remember what tangential acceleration equation is? Velocity tangential over time. So this doesn't matter. Does this matter? No.
I got it right. I circled it.
Angular acceleration.
Thank you.
Okay, so if we look at this, our omega, if we look at this circle, the omega and the when it's curving, we have to always consider the speed and the angle. Those two are crucial. All right, so the omega, the alpha are always going to be the same when you plug them all in the equation. Okay, very good. All right.
D.
B. What's the answer? Conceptual problem 2.
Line.
Conceptual problem 2. A horizontal disk rotates about a vertical axis through its center. Point P is midway to the center and the rim of the disk, and point Q is on the rim of the disk. If the disk turns with a constant angular velocity, which of the following statements about it are true? All right, so for example, let's see. So here to here is P, right? Point P, so point P is the midway, and then Q is on the rim. So Q is over here. So Q, P. Which of the following is true?
I think P is the middle of the radius.
So
I think he's trying to say it's the middle of the radius because it says between the center of where that red arrow is.
a horizontal disc rotates about a vertical axis through its center. Point P is midway. Oh, so point P, you are correct. That was my bad. Point P would technically be right there. Point Q would be there. DQ. Yeah, thank you. That actually clarifies this up a lot.
I think I have an answer.
You want to take another shot, Taylor?
Yeah, I think it's C because I know it's linear acceleration because it's on a flat plane, but I think it's C because the outside has more, it's doing more displacement than, oh wait. Is it acceleration? Yeah, it's doing more, it has more displacement or distance
Okay.
than the middle one, and the time is gonna be the same if they're in the same place. So,
is one, are either of them accelerating?
so it would be F, like,
Yeah, it's accelerated.
I'm just confused now.
No, I thought Taylor was right.
Answer would be B.
That's what
Q, if Q is on the rim and B's right here, Q is going to be moving twice as fast.
What's the difference?
So this problem is actually similar to, can we have a problem like this? How long did it take 5 revolutions? Where it was halfway. I think we did. Why am I thinking that? No. This one. How far did the midpoint of the bar travel? So we can, kind of similar, all right? Yeah, similar concept to that problem. Okay, it would be B. That's just going to be moving twice as fast.
What's the difference between B and E?
The angular velocity of Q is twice as great of the angular velocity. Okay, so angular velocity, let's look at this. Angular velocity is twice as great. All right, so velocity is going to be, let's look at this. Let's think about this. Angular velocity is equal to omega times the radius. Omega times the radius. All right, so omega for my radius. My omega is going to be the same for each one. Yeah. It's just my radius would be double.
So what's wrong with that one being right? I'm not understanding.
Wait. Yeah. The angular velocity is Q. What am I not? I'm missing something here.
Isn't omega just equal like angular velocity? So since it's constant, it's just gonna be the same. And that's why B is true, because since like the radius is double for Q, that's why.
Well, isn't it angular velocity is not how fast it's going, it's how fast it's going in a circle.
Right.
So it's the distance to like one complete rotation.
I'm missing something.
What does the answer piece say?
I haven't got that far.
Maybe if we use.
B and C. Wait.
Oh.
The linear acceleration of Q is twice as great as the linear acceleration of P.
It's not true, they use technical gravity.
Wait,
I'm
C is
sure
right too?
that holds up.
Now I'm even more confused.
So, acceleration of Q is twice as great as the linear acceleration of P.
Yeah, okay. You're right.
So, but, okay, how can C be true? Because isn't velocity.
So if we look at alpha, so alpha is equal, or acceleration is equal to alpha times the radius.
So, linear acceleration, is that
Is it more fun?
If it's good with you guys, can I skip this?
Yeah.
Yeah, we can just forget all about it.
Maybe we'll come.
What happens if this is on the AP?
Never happened.
So what? One
It doesn't matter,
Like,
we get it
it's like
wrong.
this is worth what, like 14, 10%?
This question, this is the only question that I.
That one's, I have to ponder that one for a second. I am missing something.
Yeah, I'm just gonna go with algebra.
Probably because I don't have time.
I'm drawing a blank right now. We're gonna skip that one. Last problem for the week. Example number 7. Now, I want you guys to try this on your own.
What?
Try it on your own. Now,
Honest, my bad.
you will have to do a conversion. All right? You will have to do a conversion in this one. So, revolutions per second. You're going to have to convert that to radians per second.
What about the centimeters? Do that to meters?
That information is there.
Yep, you don't need that.
I knew that.
You don't need that. So what is, if you do one revolution, how many radians was that?
Would it be negative since it's going counterclockwise?
Let's see, a 0.5 spinning counterclockwise.
For question 8, it says
No,
take counter.
no, it'd still be normal.
So, clockwise.
Oh shoot, I'm not doing this. We have to get reading.
Yes,
Yeah.
actually, none of you don't.
No.
You don't get us.
Preferably, you shouldn't.
Oh, no, I know.
Yeah, is it?
What is that?
It's slowing
Every second.
The final.
Yeah.
My calculator.
What?
All right, so one revolution, right? One revolution is 2 pi, right?
Yeah.
Okay, so I got 45. So it says, what is the angular acceleration, all right, in radians per second squared? So in alpha, so we have got to solve for alpha, omega final minus omega initial over time. So final minus initial over time. Okay, so I got negative point, I should put pi. So I got negative 0.5 pi, which if you plug it in your calculator, you get the revolution. Negative 1.57 or negative 2.
In part 8 says to take the counterclockwise rotation as positive.
Yeah.
Yes.
So would it still be negative?
No.
No.
Like it would, like our answer is still negative.
Okay.
It's talking about the omega. So
Oh.
we have the omega.
So negative 1.57 rounds to negative 2 radians per second squared. Okay. Then it says how many revolutions? Ooh, what equation? So we know our alpha. We gotta convert it back to. We gotta go to theta. What equation are we gonna use? We gotta solve for x.
Change in theta plus
Ooh.
omega times time 1/2
Change in
alpha
theta
times theta squared. Wait, not
Omega
theta
initial
squared,
time.
squared.
plus 1/2 alpha times squared. Did I hear that right?
Yes.
Okay. All right, so omega initial, that was 40. Time was 80 plus 1/2. Alpha was technically negative 1.57. Ooh. My bad. Thank you, sir. Thank you. Time squared. 80
Don't worry, I put 4 pi.
squared. Okay. So let's see. 40 pi 80 plus 1/2. 7. Okay, when you plug this in, I got about 5,029 radians. Okay, but it's asking for revolutions. So we gotta do one last conversion. 1 revolution is how many radian? 2 pi radian. Okay. So all in all, your final answer. So when you have 5,029 divided by 2 pi, I got 800.
Hold on, I kind of
800 revolutions.
I did it a different way, and I want to make sure that I didn't do it stupid, and I'm still doing it okay.
What do you get?
So I got 800. I just want to make sure I'm getting it like in a correct way. That's not just a fluke. So I took the
like highest speed and divided it by 2. Since like that's gonna be the average speed throughout.
Okay.
And then I multiplied that by 80 because that's how much time there was, and then I divided that by 2 times.
How did you get the average speed?
Because it's just the highest speed and the lowest speed, and then that's gonna be the average speed. The average of those two. It's like 40
Usually,
pi and it's
so the average. Yeah, that would work. That would work since we started from rest. Yes. But other than that, yeah, like you're spot on. Yeah. Yeah. I'll have to check that one problem out. I don't know. I don't know. I'm drawing blanks. It's Friday. I'm just kidding. No excuses. How's work last night?
It was good. I went there after school, like at 11, and then I didn't leave until 9.
Oh my gosh.
Yeah.
That's a long shift.
Well, my friend Allie was like, "Will you please stay?" And I was like, "Okay, like I'll stay for another 2 hours." Next thing I know, it was 9 o'clock, and we were closing. So I was like, "I guess I'll just close with them."
Wow.
So I love working there.
Yeah.
So,
That's awesome.
yo, are you coming in or not?
They are.
Are you coming in or not?
If I come in around like 1, I have some change in my car that I can yeah.
Lady Gaga, she's fitting off it.
That's the cheapest stuff. I don't know.
It's unsafe.
You work here?
I work today. Yeah, but I'm not supposed to, so I'm gonna have to follow up.
It depends what you want. You got a burger?
No.
Ice cream?
All right.
You just want like a phone. Like $2.
Oh, yeah, wait, I forgot.